Right, everyone, a quick reset. Last video, we focused on the mental model. We introduced each other to the what and the whys. What are signals, why they exist, and the three core primitives, which are writable signals, computed or derived signals, and effect signal. Now that you understand the conceptual layer, today we're going a step further because understanding what something is different from understanding how it works. Today's goal is very simple. That is, moving from the conceptual understanding to mechanical understanding. We are no longer asking questions like, what is a signal? But we are asking, what is Angular actually doing behind the scenes to make signal behave in a way that they do? Far, we have talked about Angular at a surface level. We have seen our three core primitives, which are signals, our hold state, computed, our derived state, and effect, our react to state. And all this conceptually makes sense. But here's the point where we shift gear. Because if you stop here, signal might feel a little bit magical in the sense that you don't declare dependencies, you don't subscribe to anything, you don't tell Angular when to update, and yet everything stays in sync. So the natural question becomes, what is Angular doing behind the scenes to make all this work? And the answer is, Angular is running a reactive system built on four core ideas. The first one being dependency. Now, at the center of dependency tracking is something called active consumer stack. Think of it as, who is currently running and interested in a signal? With this in mind, let's take a look at this example here. Whenever we update either price or quantity using the update price or update quantity method, the total signal will automatically recalculate and reflect the new total without needing any manual intervention. This demonstrates how signals can be used to create reactive state and automatically update derived values, making it easier to manage state and keep our UI in sync with the underlying data. Step number one, computed signal starts executing. When Angular evaluates total, it pushes total onto our active consumer stack. Then it goes on to step number two, where it now runs this line here. At that exact moment, it checks, is there any active consumer? And in this case, yes, there is, which is total. Then it goes on to register the relationship that is there between price and total. Then it goes on to run this line here on quantity. At the same time, it registers also the relationship between quantity and total. Number three, execution finishes. Angular removes total from the stack. Finally, the result of dependency tracking. And now we have the relationship. Now we're going to zoom into that middle box that we have in our diagram, which is the reactive graph. This is where everything becomes connected. The reactive graph is the backbone of signals. Imagine this image here, where we have got our producers as represented by signal, price, and quantity. And then we also have got our consumers as represented by the computed total. And then we've got our effect. These arrows that you see are not just for visuals. They are real relationships Angular stores internally. With this in mind, it is safe to say a reactive graph is a network of nodes that is signals, computed, and effects connected by dependencies, which we have talked about in our previous section. It is also important to note that dependency tracking creates edges, and reactive graph stores and uses those edges. For example, what happens when data has been updated? Let's say price has been updated. This means that the update price method will be executed, resulting in the following steps. A new price will be set, and Angular looks at the graph, where it will find the relationship between price and total. Then it knows that total depends on me, so it marks total as needing update. This is the power of reactive graph. Angular does not scan your whole app or rerun everything. It follows only the edge in the graph. Without a graph, that is traditional thinking. If something changes, it rechecks everything. But with a graph, when something changes, it only notifies those specific nodes. Now, with signal versioning, it is a technique used to manage the state of signals and ensure that they are updated correctly when their dependencies changes. Each signal has got a version number that is incremented whenever the signal's value changes. When a computed signal or an effect accesses the signal value, it checks the version number of that signal. If the version number has changed since the last time it was accessed, the computed signal or the effect knows that it needs to rerun to get the updated value. This helps to ensure that reactive computations are always working with the most up-to-date data and can react to changes in their dependencies correctly. Now, let us look at stale versus clean in signal versioning. Now, this refers to the state of a signal's value in relation to its dependencies. A signal is considered stale if its value is based on outdated dependencies, meaning one or more of the signal it depends on has changed since the last time it was computed. In this case, the signal value may not reflect the current state of the system and may need to be recomputed to get the accurate value. On the other hand, a signal is considered clean if its value is up to date with all its dependencies. This means that none of the signal it depends on has changed since the last time it was computed, and its values accurately reflect the current state of the system. The concept of stale versus clean is important in reactive programming because it helps us understand when we need to recompute signal and when we need to rely on the existing values. By tracking the version number of a signal and their dependencies, we can ensure that our reactive computations are always working with the most up-to-date data, and we can react to its changes with the final piece of the system, that is scheduling. Up to now, we have understood that dependency tracking builds relationships. Reactive graph connects everything. Reversioning marks what changes. Now the question is, when do things actually run? That's where scheduling comes into play. Scheduling controls when computations, especially effects, are executed after signal change. Before we dive deep, let's separate these clearly. When it comes to computed signal, it's lazy, runs only when read, and it's not scheduled. It is different with effects. Effects are eager, runs automatically, and are scheduled. So scheduling is mainly all about effects. Scheduling mechanisms determines the order in which these computations are rerun and how they are executed. That is, either asynchronous or synchronous. This is important for ensuring that our reactive computations are efficient and responsive to the changes in the underlying data. By managing the scheduling of computations effectively, we can ensure that our applications remain performant and produces a good user experience. What you are seeing here is a list of effects stacked on top of each other. And what is actually happening is that these effects are already marked as stale via versioning, they are already discovered via the reactive graph, and are already queued for execution. Internally, Angular has done something like this. Q is equals to effect A, effect B, and effect C. These effects are not just waiting to be executed casually. They are internally prevented from running immediately. Why? Because Angular is protecting you from, number one, multiple redundant executions, number two, running with incomplete state, and number three, cascading rerun during updates. So, these effects have been identified as needing to run, but Angular is deliberately holding them back to batch execution, which are synchronous and asynchronous phase or microtask. And at the bottom, we've got a block labeled multitask flush. What actually happens here is that Angular now takes the queue, iterates through the effects, executes each and every one, and then clears the queue. So when we say deferred, it does not mean that we're going to run later on at some random time. It means that we are going to wait until the current synchronous work is complete, and then we run immediately after. This gives you guarantee that all set calls will finish first. All your signals are stabilized. The graph reaches a constant. This will prevent such things like glitches. Without this boundary, you will get effects run with half-updated data. So for a better explanation, execution is deferred across a controlled boundary from the synchronous update phase into a microtask where the system is stable.